Okay. All right. So um this one's kind of a mishmash of stuff. I'm gonna start out by covering some ideas on how to measure what balance is and how to measure it from the literature. Highlight some work from the IMSI crowd there too, a little bit, hopefully. And then I'm gonna switch to a segment where review some of our lab's work on using angular momentum and changes in angular momentum to characterize balance, and then whether or not exoskeletons might be able to help with balance. And then in the last part, hopefully we'll get a little bit more interactive. I kind of want to just put out a more general framing for how we might think about stability and agility together. We'll try to derive some simple equations and think about limit cycles and whether we can use limit cycle and phase portrait kinds of thinking to define what we mean by stability and agility. Okay. So, oh, here's the sign in. If people want to sign in, I'll leave that up there for a sec. That should be enough time, I hope. And moving on. Okay. So, a paper just came out in JB that I think actually, I'm just going to use this to cover like, I don't know, 50 years worth of literature in here. Maybe not quite 50, but at least 20 years worth of literature highlighted in this paper when they review what types of approaches have been used to characterize stability and balance. That'll come in a slide from now. But in this study, what the researchers tried to do, this is from Steve Collins' lab at Stanford, was really just do a nice formal and rigorous assessment in a causal way for whether or not the common measures that we think about in the biomechanics community for balance are valid. And the way they thought about this was to design an experiment where, well, there's a lot going on in here. First, they use these perturbation experiments. So this is a system that they have called the BUMPM. It is basically like a multi-directional cable system that you can connect to a person's trunk. And when you do so, you can then apply pulls on the person's body at different phases during the locomotion, for example, and in different directions whenever you like. And then you can see how the person responds. And you can also then test what we think of as the standard measurements of balance and see whether or not they did a good job detecting a difference when the person was in an unstable, returning to stable state. So that's what I would call large scale perturbations. Then they did this other thing, which I really liked, which was sort of an add-on to the standard kit that I think a lot of people are using in balance now, which is disruption of what we think of as the physiological systems that are responsible for balance, but not in a large scale perturbation way, just in a constant disruption. So they had people walk in normal shoes, then they blocked people's eyes. People were in a harness, so they couldn't trip, slip, or fall over. They locked ankles, and then they did this really creative thing called pneumatic jets, where they would fire a pulse of air onto the swing leg to disrupt the foot placement intent of the person. And then they brought in a whole bunch of subjects, 10. They went through this protocol where they first just walked normally on the treadmill. They went through 8 minutes of random pulls, large scale perturbations from the BUMPM, back to steady state. And then they had steady bouts of walking with each of these 3 disruptions in the balance physiology. Okay, so then they drew from the literature, I guess, 6 candidate measurements for balance that have been published previously. You've got to go read the paper to get all the citations. I'll mention that the step width or the step placement predictability measurement was motivated by a lot of Nidhi Siddhipathi's work, who's part of our group. I'll touch on that in another slide or two. But let's just go through these. So the first one is where people put their step in the frontal plane. So step width. Next one is step time. How quickly does the foot return to the ground after the perturbation coming out of a swing phase? This next one is called step placement predictability. This is based on a model that if you know the center of mass, position, and velocity in mid-stance, you can use a linear map to predict where the next step is going to go. And that's a hypothesis for what kind of control humans and other bipeds, maybe even things with more legs, are using, right? So center of mass based step placement. Then they checked, this is called like Lyapunov exponent. So if you plot the gait, the center of mass trajectory on a loop, like a phase portrait, and there's a disturbance, you can measure how quickly the system returns to the nominal sort of trajectory, and this could be in 3 dimensions or 2 dimensions, however you define your state. Next one here is margin of stability. This is based on the idea that if I know how fast the center of mass is moving, I know where a foot needs to go to keep me from falling in the time that it takes to take a step. And if my foot falls within that boundary, then I'm safe. So a small margin of stability is good. And this one's been in the literature for a long time too. And then this really simple measure of like how far the center of mass deviates from some steady position. Okay, so they evaluated these 6 criterion, and they're looking for changes in response to either a large scale perturbation or changes in response to those steady changes in the balance system. And what they found was pretty interesting here, that the accuracy of each of these 6 measures to detect the perturbation or the unbalanced state was metric dependent, right? So if you look here on the left, you can see that foot placement predictability seems to be outperforming kind of all the measures globally. Surprisingly, these sort of ideas from Lyapunov exponent and lateral margin of stability don't perform as well, which was surprising to me. And if you just look at center of mass displacement, you're no better than chance. Like you might as well just be guessing. If you just observe the center of mass displacement, you wouldn't be able to tell whether someone was unbalanced. Okay, so
do you want discussion or questions in between, or do you want to wait?
Sure, yeah, go for it.
So Lyapunov exponent, can you explain what it takes into account? Because from my understanding, it's really like how much it diverges from one step to another. Is that right?
Yeah, so I think you what you do is you make the phase portrait. So let's just say you plotted the X and Y position or the 3-dimensional position of the center of mass over a gait cycle. It makes some pattern, which they're drawing this as this ribbon thing, right? And then when there's a perturbation, usually what you do is you pick a point during the gait cycle. Some people refer to that as like a Poincare section.
Yep.
It is a slice through the trajectory, like on a plane. And then what you're looking for is over the next some number of steps, as the state passes through that plane, how close did it come to a bullseye, which represents the steady state limit cycle. And then what you're measuring is the exponential decay of the system over steps back to that point. That's my understanding of
Yeah, that's what I think
works.
it is too, and I think it has a lot of assumptions on it that about periodicity and what's good or what's bad, because like a lot of things like center of mass displacement, like people don't come back to exactly where they started, and it's okay. So that's
Totally.
where I think that people with better balance might actually not come back to exactly the same place.
Yeah, they could just find a neighboring stable limit cycle, and that would be okay too, right?
Yeah.
So I agree that like this technique doesn't take into account strategies that might like just find another limit cycle that's just as good. Um, and maybe
And
that's part of the reason it's not so good here at detecting whether there's imbalance. I don't know the detail. I didn't
but
read the
like
careful details
we were
as
talking,
homework for
yes,
this
but this is
segment, but
also based on a steady state assumption, which
yep.
like when we were talking about running down a mountain, like you are definitely not at steady state. And like you manage non-steady state really, really well, versus someone who kind of needs the steady state to be able to manage that. I think those are two really different strategies. Um, and I don't know how
Yeah,
that shapes up on a
that's
Poincaré
an
study.
interesting point. Like
Mhm.
it does seem like all these definitions kind of originate for the assumption that things are steady to begin with,
And
right?
that's desirable, right? That steady state is the
That
desired.
right,
Yeah.
that's optimal or desirable, or
Yeah.
that's like the chosen state of things. But
Mhm.
Lena's example about downhill is a perfect example of there is no way step to step I'm in a steady limit cycle going, well, you could be, but you're most often not. And you're just dealing with interactions in the environment to help you stabilize, which is, it's more
Because
like,
every step is different in terms of the interaction with the environment, right?
yeah, and their environment's changing in real time too. So like you're going to pick maybe a soft surface versus a hard surface from step to step and so forth. So totally agreed that this setup in this experiment doesn't handle a lot of these real world edge cases.
Yeah, the
What
other
I
is
do,
like with a
yeah,
lot of those measures, they require you to walk for like a minute and they look at stability, but the reality is that it's always going to be stable because people aren't actually falling down or going away. So it's not necessarily, I don't think it's necessarily a probe of people's balance. It's maybe a probe of their gait variability.
Yeah,
agreed.
and the
Good
question is
points.
whether that's functionally meaningful or not,
Yeah, I
right?
mean, like in Parkinson's disease, it is. Okay, so,
Mhm.
but it doesn't mean that, um, it doesn't necessarily
Well, I
predict
mean,
like
it
falling or
does put a
balance.
wrench in our ability though to define things that are universally appropriate for measuring, say, stability under different contexts, right? It might really need to be very context dependent. Okay, I'm gonna keep going.
Yep.
Um, so I just wanted to say a little bit more about the step placement predictability idea. And this really comes from Manoj Srinivasan's lab. This is one example of a paper from their group that Nidhi Siddipathy published on running, but there are a number before this by Varun Joshi, and I'm not remembering all the other authors. You can go to Google Scholar and find all of them. There's probably like 4 or 5 good papers in a row. And the idea here is that if you just look at this cartoon trajectory over here, times when the trajectory is blue is when there's a foot on the ground, and in red is those are aerial phases. The general idea of this um, framework is that, especially during walking, but I think they also show evidence during running, that right around mid stance, if you take the center of mass velocity and position, so the center of mass state, and you relate it to where the next footfall goes in the next stride, there's a very strong linear relationship between those things. And that's pretty cool because it suggests that a very complex locomotion system that's got all kinds of nonlinearities might basically it's balancing actions can be explained by a simple, you can fit data to find the mapping between um, state in the middle of the stance to the next foot placement. So I just wanted to highlight again that this seems to be a thing that lots of data fit to, and also turned out to be have the highest predictability in the measurements that I presented on the last slide. So maybe 2 checks for. Another idea that's floated around for a long time and that we've been exploring in our own lab as well is the idea of angular momentum regulation during walking. So like just from physics, this makes a lot of sense that you want to regulate your angular momentum to be on average around 0 when you're moving so that you don't pitch to the ground, right? So angular momentum is the sum of all of your segments and how they pitch and how the pitch velocity changes over time. And the moments that you place around your body's center of mass with your feet on the ground are constantly regulating that angular momentum. So the sum of the moments on the ground come up to the change in the first derivative of the angular momentum of the body. And this paper pitches the idea that there actually may be, I think it's actually sort of a requirement. It's kind of no surprise to me the physics say that this should happen, but that you're putting your foot in places on the ground to create moments around your center of mass that keep your angular momentum centered around 0 change. Okay. And that's kind of nice because it maybe then motivates the idea of using angular momentum as a way to measure how unbalanced or how quickly someone's returning to a balanced or regulated angular momentum state. And then for a long time in the literature, this is work by Anne Silverman. I wanted to highlight her stuff here. People have used angular momentum most of the time, though, in steady walking again. So there's not a perturbation here. People didn't really check to see whether the angular momentum hypothesis worked in large scale perturbations till pretty recently. But what's cool about this is that even in steady gait, you can notice changes in the sway or the fluctuation of the angular momentum that seem to have some relationship to populations that might suffer from imbalance or falls risk. So one example here is from amputees that Anne published. And you can see here the angular momentum in frontal, transverse, and sagittal planes for amputees and non-amputees at different walking speeds. That's what the different colors are. And what you can already notice from the frontal plane, which is usually where the most fluctuation happens, is that at these slow speeds, amputees have a much larger amplitude of swing in their frontal plane angular momentum than non-amputees. And then that is all just summarized over here in these nice metric graphs that show a clear difference between amputees and non-amputees and in the way they're regulating their angular momentum just during steady locomotion. Okay, so that's some evidence and support for the idea of using angular momentum as a way to measure balance as well. Okay, so now I introduce a number of concepts now. We put 2 checks against foot placement, predictability as one way to think about measuring balance and return to stability. And then also I just mentioned angular momentum, and I'm gonna stay on the topic of angular momentum for a little bit. Another couple points to make here. So like, I feel that only studying steady state locomotion, Lena already kind of alluded to this, it's not the best way to get at how people balance. We should be pushing on people and checking their perturbation response. And I think that hasn't really been a common theme in the literature until pretty recently, with the exception of standing balance world, where they've been doing this for ages because they're smarter than locomotion people, maybe dynamic locomotion community, or maybe the experiments are just difficult for a person walking to apply large scale perturbations. And now we finally have the tools where we can do this. But I think we should really be, if we really want to understand balance and stability, we've got to push on the system or give it obstacles or other challenges that push it out of its steady cycle. And in our group, we've been trying to do this in a number of different ways. I don't have time to go through all of this stuff today, but if you're interested, you can check out some of the work by Taylor Dick when she was in my lab, where we just had people hop vertically and then change the substrate height on them and check to see how they're, in this case, we weren't looking at angular momentum, we were using mechanical energetics, which I'm going to argue could also be a nice way to think about balance and stability. Other things you can do are like slip a treadmill belt. I'll talk a little bit about this in a minute. And then sliding platforms. And this is a case where we slid a platform during standing balance, but I'll show you in a little bit too that we now have techniques where we can slide the rug even during dynamic locomotion. So I just want to talk first a little bit about standing balance, and this is work with Lena that we completed a couple of years ago now. The question here was whether or not if we gave an assistive torque from an ankle exoskeleton during a backwards perturbation that would pitch the person forward, could we keep them from taking a step? Could they handle a perturbation? Another way to say it is we evaluated balance by asking how large the perturbation would be before they needed to take a step. And we hypothesized that if we gave them an ankle exoskeleton with timing that was faster than the human's nervous system response, that they would be able to withstand a larger perturbation before they took a step. And so here's just some simple depiction of the protocol. Quick surface displacement, and then the red and blue are exoskeleton torques, which we purposefully applied as fast as we possibly could after the perturbation onset. The exoskeleton knew when the platform was going to move, so in that sense, we were cheating. We told the exoskeleton to turn on as fast as possible in concert with the slide of the platform. Doing that in a real world system would be a little tougher because you would need to detect something, but this was a basic science question. So you can see here we come on artificially fast, or we delayed to be around the latency of the human response. In the gray black background here is what a normal torque response looks like for a human reacting to this. So we just aligned the exo with the human's intent, or we made it go faster. And so here's what it looks like. There, the exoskeleton is on. You can see a much more extreme plantar flexion in that right video. And people are able to sort of swing their center of pressure out toward their toe much more quickly, which may be a part of the reason they can balance better. And so what we did here, this is just another approach to measuring balance that is more commonplace in the standing balance world. Would be a lot more difficult, I think, to do this in walking, because it's very hard to make people, it's very hard to apply perturbations of different sizes in a randomized way during walking that makes this approach viable. I think it's a little bit easier during standing. But the idea here is you just keep giving them a larger and larger perturbation with random small perturbations interleaved in until they take a step, and you can fit these psychometric curves to their data to figure out where the 50% breakpoint is. And then that becomes your measure. It is a size of perturbation that causes more than 50% steps. And what we found when we did this was that only in the condition where we gave the exoskeleton assistance faster than human, were we able to affect the balance, which was pretty cool. And then there's a whole, you'll need to go read about this. I didn't have time to talk about it today. There's this idea of global rather than local. Looks like I forgot to paste the key figure in here, but I'll just tell you the punchline. We measured EMG and ultrasound around the ankle. And what we found was that in the very fast exoskeleton strategy, we actually reduced the amount of stretch in the calf muscles, and therefore probably reduce the local neural response. We can see that in our EMG data, and still people were able to improve their balance. So what that suggests is that people are maybe using this global center of mass level strategy where they use all the sensors in their body to estimate what their center of mass is doing. And then that center of mass estimate is then used to farm out the control. Kind of like what I was just talking about earlier with the foot placement predictability idea that Nidhi and others have put forth, maybe a generalizable principle for balance. And yeah, our anecdotal results from this standing balance experiment suggest that that might be happening also. Okay, I'm going to pause there and see if people have questions, comments, feedback so far. Maybe not.
Hey, quick question.
Go ahead.
Yeah.
When they're farming out control, did you find that the strategies were consistent with an individual?
Lena can probably speak in more detail to this because she's got a number of papers on sort of stereotypy and balance response. The short answer is definitely not. There's a lot of flexibility in how the center of mass states lead to both motor control, so EMG, and also joint torques in the lower limb.
Yep.
What I can tell you is that this is work by Kristen Jakubowski that I'm talking about now. I don't have a slide on it, but she's taken Lena's idea of a sensory motor response model, which is the idea that you can take the center of mass, acceleration, velocity, and position and map it to EMG responses in the leg. Kristen converted that to map to torque responses in the leg. And basically the model fits that you make to each individual's data come up with different gains. And so what that suggests is that there are definitely individual differences between people and sort of how they map the center of mass state to their unique response. Lena, do you want to say more about that?
Yeah, I mean, we did it in standing balance, but then Martin Ashrift and Friedel de Groot actually translated it to joint torques during perturbations to walking, actually before we did, but they were looking more at just the amount of torque. And that is interesting because it's different because that one applies to the stance leg and not the stepping leg.
Yeah. It's a teamwork thing. Yeah.
But as far, I think you were asking about the strategies, are they individual specific?
Yeah, because you're getting like just building on what you said about farming out the control. So there's a detection and then there's a strategy and the distribution of, if you would, in terms of say ankle, knee, and hip moments to achieve that overall whole body response in terms of angular impulse response. I'm guessing that might be unique to the individual.
Yeah, so we definitely showed that in people during the standing balance. Maybe not at the torque level yet, but definitely at the EMG level. And so
Okay.
I think yes, so it should apply to the torque level. The other interesting thing that's anecdotal and maybe we haven't published is that like when Jenny did these things, sometimes when people get moved laterally, they like will take a step or they'll hop or they'll jump. And we once had a study when we were perturbing people in multiple directions and they had to take a step to recover. And I really thought this was an error because like some people were taking a step with their right leg and some people were taking a step with their left leg for the same direction of perturbation. And I was like, this can't be true. So, but it was like some people were doing this like step out and other people were doing a crossover step for the same direction. And it was highly repeatable and specific to the individual.
So that gets interesting from the reaction force generation that came from that, right? So going back to the net angular impulse idea, right? You've got two operators here, you've got two legs, and you have a center mass trajectory. So the moment arms and the relative contribution of each leg gets really interesting. So that's why I was asking that. Yeah. There might be something there.
Yeah, and I don't think the step placement and the stance like joint torque thing have really been combined to kind of look at, okay, how do I distribute the balance correction here between the stance leg, which is going to be bringing you back to kind of the original trajectory, and then the step leg, which is basically creating a new equilibrium point or trajectory for you to go around.
Yeah, just a bit more anecdotal discussion on these points. Jill, one thing that we see I'll talk a little bit about Jenny's experiments in a minute, and you'll see this on a pie chart in a slide or two. But like when people get pitched so that their new stance leg is interfered by their current stance leg. So one example of this is I'm about to take a step on the ground with my right leg, imagine, and I get pitched backwards and leftward. So I can't get my leg through my other leg behind me.
Right.
And what people who are, I don't know if we'll talk about what agile means later if there's time today, but
Oh, good.
some people recognize this for whatever reason, and they hop on the
Yeah.
current stance leg backwards and leftward to put. They can't
Yeah.
get their new stance leg there. They just use their current stance leg as a pogo stick,
Yep.
um,
A
which
great
is pretty
plan
cool.
B.
Like it
A
is
plan B.
definitely, yeah. Whether or not that comes from their center of mass detection and farm out strategy, I mean, who knows? But it's
Yeah.
a pretty unique strategy that is. We see it across multiple individuals, so it's not like, oh, that person's a hopper, you know.
Yeah, we see it in a lot of sport related activities, right? Because something's blocked, that method or plan A doesn't work anymore. So the anecdotally, the people who avoid
Yeah.
injury are the ones who have good plan Bs in uncertain circumstances. So we've seen stuff and behavior in this space, so I'm not surprised by it, but it's great you're detecting it
Yeah.
in a much more controlled scenario. So this is great. Thanks.
Okay, I'm gonna keep going.
Yeah.
So we'll come back to the whole body angular momentum idea now, but this time we're gonna think about larger scale perturbations during walking. So remember I mentioned that folks have been using angular momentum regulation to look at differences between, say, populations like amputation or Parkinson's or stroke during steady state walking. And the idea is that if the swing in the angular momentum during a steady gait is large, that system is more unstable and might be more vulnerable to falls risk. And like I mentioned, I think that that's nice, but it would be good to know whether or not that same system that has angular momentum swing nominally also has trouble responding in terms of angular momentum regulation to large scale perturbations. So that's what we tried to do in this experiment that Jenny led a few years ago now in the lab. And a key thing was to be able to use this Karen system that we have, which is the treadmill is now up on a Stewart platform. So we can pretty quickly trigger a acceleration velocity displacement perturbation that is phase locked to the gate, and we can do it in multiple sizes, and we can also do it in multiple directions. So we think about this sort of around the whole clock. And then we can observe the whole body angular momentum pre, during, and post the perturbation and check to see how well a person's able to bring their angular momentum back to some steady is the idea. And so that's kind of pictured here. You have some, and this, by the way, we'll talk about this later, but I don't think it needs to be angular momentum. Some representation of the state that you can observe would be good. You apply a perturbation, that thing gets kicked in some way. And now maybe a lot of you are thinking about if you took system dynamics or like spring mass mechanics, you hit, or any second order system, you hit it and it sort of comes back to some steady nominal cycle after some time. And then you can measure things like how quickly that happens, how much overshoot there was, et cetera. So this thinking of knocking people off their steady, I think is useful because we have a lot of analytical tools to come up with metrics for how well people return, and maybe those are related to stability. So Jill, this is what I was talking about before, these little red. So let me just first describe what we've got here. This is sort of a qualitative look at a large data set. People went through 96 different perturbations that covered lots of magnitude, directions, and phases. And here we're trying to distill that down into a sort of an infographic that that categorizes how large the disruption in the angular momentum was in response to different types of perturbations. And so what you can see here is that, I don't want to go into all the details, but there are a lot of situations where you get very large perturbations from different timings, but there's also these key things where people do things like jumping, and they come up with strategies that have one leg leave the ground, for example. And so we can categorize that over sort of all the perturbations. More importantly, these are the kind of data we get. So this is in the sagittal plane. This is the whole body angular momentum. The black curve is what you would observe during a steady gait cycle. And the colored curves represent shifts in the angular momentum due to the perturbation, which is here in the vertical dotted line, due to different directions of the perturbation, which are color coded here, okay? And what's cool about this is you can see that the experiment does a really nice job of dose response modifying the whole body angular momentum response, which is really nice. It gives us big data sets to work with. This is the perturb step. We can look at it in the next step also, and you can see that system's not back to normal even after one step. It's a multi-step process. This is what it looks like in the frontal plane. Again, really nice variation in what we can do to the frontal plane angular momentum, how we can perturb it, both on the perturb step and on the recovery step. So then the question then is like, okay, well, what do you do with these data? What do they tell you about balance or not? I think that's still an open question, but our thinking is that what we want to look at is multiple steps and check to see how far the system is from black, from the steady, and then define some criterion by which we think the system is back near steady, and then measure the time maybe it takes to get back there, or the number of steps, or something about time. And maybe then now we're starting to get at something like a more generalizable or standardized metric for stability. And there's a lot of chinks in that armor, I realize, but that's sort of how we're thinking about it in the lab now. And then what do you do with that? Well, if you can, if the data without an assistance or a clinical strategy or a training suggests that that's a valid thing to do, valid thing meaning use the whole body angular momentum measured against steady, so the steady state error in that metric as an indication of the current level of imbalance, then we should be able to estimate it and use it for feedback control. Maybe that's what the nervous system of a person's doing. I think that's what her and Popovich would claim, right? That there's some kind of momentum regulator somewhere in the nervous system. And if we could generate estimates for that angular momentum on our own and then feed them into either a biofeedback training program, or in our case, we would love to do this in an exoskeleton, maybe we can, just going back quickly here, take this green curve, for example, maybe we can attenuate this deviation from black by intervening with an exoskeleton to apply the right torque, to put the foot in the right place, or regulate the center of pressure. So the idea is control strategies that collapse colors to black. Okay. I'll pause there and see if there's any questions, comments. Jill, I see your comment. Do you want to talk it through?
Sure. So the way we've thought about this in well-practiced goal-directed tasks are really looking at regulation of linear and angular momentum. So we're really looking at how the individual or opportunities to produce angular impulse, for example, recognizing there's more than one way to achieve that, especially if you've got two legs on the ground, you've got a center mass trajectory, and you just think about center mass position relative to feet. There's a position vector, you've got a reaction force with magnitude, direction, and you have time on the ground as an impulse, right? So when you look at Antonia Zafiriou has done a lot of this in dance and other things. We've done stuff in golf, which is a dynamic balance perturbation, if you think of it that way. But you get to see what the role of each legs are and how individuals solve the problem. And what we're finding in these, again, goal-directed, well-practiced tasks is individuals will have different solutions, which gets very interesting. That was kind of a basis of my previous question. But it does characterize where their priorities are. And then some nice things that Antonia did is she looked at single, double, and triple turns. So she was able to see if you need this much angular impulse, what do you do? But if you need more and more, where does that come from? And so this is the management and the regulation of it, and having strategies to amplify, and this would be similar to speed or any other performance objective. But there's at least what we've seen is there's individual differences here to pay attention to, and there's more than one way to get the same regulation. So that's my, yeah. So this is really great to see what you've got here. Thank you.
Yeah, I mean, I think just to piggyback off that, what that might mean is that this generalizable idea isn't generalizable, right? We need to pay attention to an individual's baseline balance response and feed that prescriptively into their tailored intervention, possibly, right?
Yeah, because these are
So,
control choices that they're making, right? And it,
mhm,
they might be their personal, you could have a situation where they weight that high in terms of their control logic, but it may not work
mhm,
for them, right?
right,
So that might be their go-to, but it may be also the source of the problem, right? So it could be that you use that knowledge about that individual's, and then you figure out, well, that's not going to work in these circumstances. There's a need for discovering an
yeah, exactly.
alternative. So that's where the
And maybe
intervention
there are
personalized.
sort of categories of response to, like,
Yeah.
if you could identify who's a jumper versus who's a center of pressure stabilizer versus who's a stepper, then, and I think that's what you're saying, maybe populations fall into categories like this, possibly. That would make it a little easier to deal with the individual variation, right?
And I think the ability to hop on one leg while off balance is not always available to everybody. So this is the part where we talk about
For sure.
individuals' capabilities to move into a plan B with that is, you know what I
Yep.
mean? Like that may not be available to everyone because
Yep.
of their capacities.
Okay, I'm going to keep going. Yeah, so again, the general idea here is bring folks back onto the cairn, but this time with a device where the device is, what we're trying to do actually is use some machine learning techniques to forecast what the joint moment response will be sometime in the future, and then pull that anticipated response to now. Again, trying to be faster than the human if possible, right? And this is, I don't know, it's a challenging problem. We'll see if we're able to pull it off. Okay, so I want to talk about another perturbation paradigm that we've been using, which is belt slips now. So this one is, I would say, more common than the slides during walking, just because it's a little bit easier to do in the lab. But all you do is and again, you can control the timing of this. That's what I'm showing here. We did this during early and late stance of the stance leg. We accelerated the treadmill belt backwards. And by doing it at different times, you can control the mechanical energy flow from the treadmill into the leg to make it either inject or absorb energy. So if you slide the belt during the braking phase of the gait, what you do is you take energy and put it into the leg. So now the system's got to deal with a higher level of mechanical energy in the ensuing steps. If you wait until late and you slip the belt, the treadmill is sucking energy from the leg. So you put the person at an energy deficit in that case. And that's kind of cool, because then you can set up the question like, how do the neuromechanics of a leg deal with energy surplus versus energy deficit? And so that's what we try to do in Paul's work. And I don't want to belabor the details here, but what we were able to do is an inverse dynamics analysis. And then we could see which of the joints handled the whole leg energy change best. And what we found was that the contralateral knee, so if I slip your right leg, your left knee's next step is where the action seems to be happening. Now, whether or not that's, a generalizable fundamental truth or has to do with this specific perturbation, we're not sure. But it sets up a pretty nice framework where we kind of know how the joints are dealing with an energy change imposed on the body. And then what Paul did is he built a hip exoskeleton. You can see the belt's going to slip here. What we're hoping this device does is help get the person's swing leg out in front of them faster after the belt slips their leg. Okay, so if I have a spring that's on the front side of my hip, and the treadmill pulls that leg backwards, what I do is I load that spring, and then the recoil that is now in that spring should be able to accelerate the next step of that leg and provide a stabilizing response. So that was the idea. And what we found, basically, I'm going to speed through these. And again, this is just another approach. Instead of using whole body angular momentum now, we're summing the joint energies in the leg. And we're asking when the leg joint powers come back to a steady state cycle rather than the momentums of around the body. And I kind of like the energy accounting a bit better because it handles both internal and external energy flows. The whole body angular momentum really only handles segment energies with respect to the center of mass. You would need to do something like Jill said and add linear momentum into that to really capture everything. If you go straight to inverse dynamics, you capture sort of all the internal energies of the leg and the part of the energy that goes to drive the center of mass all at once. So it's a 100% pie that things kind of need to add up to from energy thinking that we like. And that's just another approach to thinking about stability. So here again, this is what the whole body angular momentum looks like. We weren't able to really do much with the exoskeleton post perturbation. We did make the angular momentum in steady state fluctuate more, which, you know, the community would say you made someone's fall risk go up when you put a spring on their body because their whole body angular momentum had a larger amplitude in the steady state. So we don't know, that's possible. The key thing that we were looking for is here whether or not the springs of different stiffnesses can reduce the whole body angular momentum below this black bar, which is the amount that the whole body angular momentum changes due to the perturbation. And the answer was no. So that was kind of a bummer. And then we also looked at the mechanical energetics just to check another way of measuring stability. And we also found the answer that no, none of the exoskeletons were able to attenuate changes in the mechanical energy due to the perturbation. This may just be because it's a passive device and it's a spring and it's not able to modulate mechanical work sort of on an optimal timing. Okay, so I'm going to pause there again. We're going to go into a more interactive whiteboard sort of part of the talk in a minute, but I want to leave it here just to see if folks have any thoughts, comments on which of these approaches for assessing stability / balance you've used and which ones you like, what are the trade-offs, etc. We can spend a few minutes talking through that if folks want to. Okay, it seems like the crowd is dead. So I just want to, before moving on to the next part, like there's a few key things that I think I've taken over the last 5+ years of starting to really think about balance in the lab. One is, I don't think you really know much about balance unless you study perturbation response. And so that's sort of I think a key hallmark. If you want to study balance, you can go ahead and check things in steady state, but you probably should push the system and see how it responds if you want to say anything about level of imbalance or whether certain scenarios are more stable. And then the other thing is that accounting for the center of mass mechanics in some way seems to be important. And I'll say that based on the idea that there's mounting evidence that there's something special about center of mass state orchestrating the balance response in legged systems. And so we should be thinking about, at least as part of our cocktail, maybe not just fluctuations in energy around the center of mass, but also what the center of mass itself is doing. Okay, so let's go on to the next section here. So what I want to do next is try to use a simple model to think about a way to define stability, but also bring in the idea of agility. Like what do we mean when we say stability versus agility, and how might they be different? And so I think I've shown this model a bunch of times in this community before, but we're going to use a simple vertical hopping model. Like I said, it lets us look at the center of mass mechanics directly. Just imagine a mass moving up and down and being driven by a ground reaction force. And in this case, I've got a muscle tendon unit that's driving the force on the ground. That's not going to be really that important for what we go through in the next number of slides, but obviously I'm interested in muscle tendon units. So the actuator that drives the center of mass that we're going to think about is going to be a muscle tendon unit. Okay, and then what this simple model does is it takes a square wave input as sort of a nerve signal on a feed-forward clock, and it uses a Hill-type model to turn that into activation, and then it uses the length velocity, the force length and force velocity relationships to derive what the force is at any given time, and then that gets pushed through a tendon. And the tendon can then modify the length and velocity that the muscle sees in ongoing hops, and that has an effect on force and work output. Okay, so that's basically the framing of the model. Now, how do we use a simple model like this to think about not just stability or economy or agility alone, but maybe the trade-offs between all three of them is a question that we've been working on in the lab for a bit now. I'm not going to spend really hardly any time on the efficiency part today. We're going to talk more about the stability and agility parts. But one thing I want to emphasize here is that all three of these things, the way we're going to talk about them today, are defined using energy. So like mechanical energy is at the core of this. And I think that that's important. You could also do the same thing with momentum, but we're going to stick with energy because we can then relate amounts of energy across the domains. How much energy did it take to make an agile maneuver versus how much energy did it take to dissipate an external perturbation, for example? And then how much metabolic energy did it take to drive the mechanical energy in a limit cycle, right? So this idea of common currency of energy, I think it makes it nice to then think about multi-objective systems where we might want to sort of have our cake and eat it too, do well at all three. Okay, so I already talked about this a little bit, but let's focus on stability and agility now. What I want to get to is the idea that stability is from an established limit cycle, which we'll try to draw out in a little bit. But you can imagine a circle, and the system is going around a circle that represents its position and velocity. If the environment or some unexpected momentum or energy knocks that system off of its steady cycle, we can think about how long it takes for it to get back to steady. Now, Alina's already going to raise her hand and say, wait, 20 minutes ago, you agreed that you can go to a different limit cycle and that would be okay. For today, the experiment in the lab is that a person's on a metronome and they're hopping to a certain height. So we've set their steady state limit cycle and they've been instructed to maintain it. So their task level goal is stay on that limit cycle, okay? And what we want to understand is whether different setups of the muscle tendon unit and nervous system do better at getting back to the limit cycle fast when a perturbation comes. Okay, so keep that idea in your head as the notion of stability. What do I mean by agility? So now agility, I would like to argue, is different because it involves a volitional change by the animal, or could be a human animal, by the robot, by the system, to move to a defined other limit cycle that's not at the same energy. So now the experiment in the lab is I'm hopping in place, I'm following a metronome, I am height locked, and I either change the metronome beat or I change the height that you need to achieve, or both. And I ask how quickly the system can get to that new task, which is a limit cycle that exists at a different energy level. I could also do that at a lower energy level. I could change the frequency and amplitude of the cycle to either have more or less energy. Okay, so pause. Any feedback on those ideas?
Greg, until I had a conversation with Lena at CMB, I would have totally agreed with that definition of agility. But then Lena challenged it and said, what about slalom skiing? That's definitely an agility task where you're basically trying to keep your center of mass dynamics basically kind of very smooth and your legs are going crazy underneath you, right? And so in that sort of example, you would need to include, if you want an energy-based agility metric, you would need to include internal energy flows or something like that, right? To maintain a desired trajectory given external perturbations away from it.
For sure. So I would flip that and say that's
Mogul
stability,
skiing,
not
not
agility.
slalom skiing. Yeah.
So like you're using agile maneuvers of the leg to maintain the energy of the center of mass within an envelope. So I would actually call that stability. I think that falls under my stability category more than the agility one. There's totally a gray area here, I get, but the way you described the task goal was like basically keep my position constant and my velocity within an, right? Like the relative position of the ground contact to my, well, how should I say this? If I were to draw sort of the limit cycle of that, your average position is going downhill at a constant velocity, and you're trying to keep changes away from that position and velocity to a minimum. So it's almost like standing balance in a moving reference frame. And in that case, I totally agree that you want to look at not just the energy on the center of mass, but the internal energy exchanges between the segments become important. I think that gets captured by a full leg inverse dynamics approach to characterizing the energy, maybe.
Well, I have a comment about inverse dynamics though, as well, which is
Yep.
if you're looking at a joint level, you're not actually capturing all of the relevant energy flows because there are multi-articular muscles in the system, right? And so if you really wanted to capture all of the relevant energy flows, you'd need to consider the exchange between like the biarticular hip and knee extensors versus the, multi-articular distal limb muscles, right?
Yeah, totally. Yeah, the biarticulations are definitely not handled true. I think you can still see a little bit of exchange between joints, so that's something that gives
But
you a bit
sometimes
more
you do
about.
get a very
Yeah.
false impression of, for example, the amount of power that's actually generated at the ankle, which in reality might have been generated by proximal muscles and transferred basically downstream, right?
Totally. Yeah, I mean, it is conceivable to do all this stuff in a model that has complex biarticular muscles too, right? I mean, I think
Yeah. But that gets hard because you have
what
to optimize it, things like that, right? To get the
for
solution.
sure. I guess I'm just trying to advocate that looking at the energy isn't a bad idea, and thinking about how the energy is regulated maybe isn't a bad idea, because it might help us talk across the agility stability line and kind of maybe there is a continuum of when behavior switches. Another example is like when when a person first receives a perturbation on the Karen, there is a time period after that which I would think about as, oh, it's a stabilizing action. But then agile maneuvers might be used to stabilize, right? It's kind of like, especially if it's a multi-step process, like in that first step, if I'm still at an energy difference, now I'm like, now I've had enough time to volitionally decide. I think that's the key thing. Like, it's not the automaticity anymore of intrinsic mechanics or reflexes. Now I've got volitional feed forward control that I can change. Then the line between stability and agility gets really blurry because I'm using agile maneuvers to stabilize at that point.
Right. So I think sometimes there's a lot of language that suggests there's like a direct trade-off between stability and agility or something, but in fact, there's a lot of overlap, right?
Totally.
And
Yeah.
agility also gets into this idea that Jill was mentioning about capacity, right? Like if you have more capacity, then you're going to be more agile, but then you'll be able to use agile maneuvers to maintain stability across like a wider range of possible energy states and limit cycles, right?
Yeah, totally. I mean, I think, yeah, there's definitely no hard
Yeah.
line.
I think also there's also like a lot of people like Jill and sports people have ideas about what agility is, and I want to make sure we don't make a definition that is like not considering those. And that can apply, or you think about agile business practices, right? It means you can change quickly without expending all of your resources. So there's some balance there, right? I was just thinking about it. What does it mean? It means like it shouldn't be all about power, or you want to be nimble, like you know, where does
I mean,
nimble?
another thing that, and this comes from conversations that I've had over the last few weeks with people like Madhu Venkadesan when I saw him at AMM, and Lena and Monica at ISB and CNB. I think there's also, in my mind, there's a struggle between thinking about impulse momentum, which only considers the velocity or the kinetic energy parts of the system, versus thinking about work energy, which can, in the case of a system that is a terrestrial animal on Earth, there's a gravitational potential there. There are springs potentially in the leg that can be potential energy wells. And you can imagine a case where a muscle tries to respond in an agile way, and it doesn't show up as an immediate change in the kinetic energy of the center of mass. And I'm not sure it's okay to call that agile, because the acceleration of the body, the change in momentum, may happen a bit later because these storage elements can then shuffle it later. But the immediacy of the response doesn't show up at the center of mass directly, right? So I think a key distinction between momentum and energy is that the energy approach captures the energy inputs from the muscles completely, but it doesn't, you're not agile if you stand in place and quickly load energy into your tendon, right? Until the center of mass is moved. Anyway, I'm not sure if that's right or not, but there is that complication in terrestrial systems where the potential energy is a thing, and sometimes the agile task is to just straight up change your potential energy to like jump up a ledge. And it doesn't really matter whether or not well, you have to ask yourself whether or not it matters that that happens quickly. And then if it matters, if agile means being quick, where is the fair time to start the clock? When energy is released from tendons onto the body, or when the animal first turned on its muscle? So again, more food for thought, right? So I think it's,
I feel like we could
Jill,
have
what would you,
write a whole paper on what is agility of this.
wow.
Hash
Here's
this
what
out.
I would
Actually,
say, just that the Venn diagrams are really a valuable thing here. Because right now you have the circles as equal circles, right? And you're looking at the overlaps, but in different tasks, like energetics may not be the most critical thing, but the agility might be. So if you use the Venn diagram, you're acknowledging there's overlap here. There's not always clarity about where the endpoints are of these things, but it allows for things to matter more or less depending on maybe the task objective. So I really like that because this is what we'll figure out together, right? So it just might be they're not always equal in the Venn
yeah.
diagram.
Yeah, no, I mean, in my diagram, but I wasn't, hopefully, I was trying not to signal that they should be equal, but that just, and
Oh,
then you
totally
can
get
also
that.
imagine, okay. I think you can also imagine a like objective function in optimization that has three terms. That's what I'm trying to think about longer term, is like, if I have three terms in an objective function, let's say I want to create a system that's specialized for agility. I'll just turn the weights to the two things that are not agility, stability and efficiency, to 0. And then I'll ask my computer to tell me which muscle tendon unit wins at the game of agility. but we need a definition for agility in that simple system, right? Which is kind of, that's part of the difficulty. Jill, while we've got you here, and since you've thought about agility for so long, how do you think about it in your lab? Like, what is the measure that you can get behind the most, would you say?
So I have the advantage of having well-practiced goal-directed tasks. Like, what are you trying to achieve is defined. It's kind of like you're hopping to music or rhythm or something, right? And then you're allowing choice, how you're going to achieve that, stay on beat with your metronome, right? So what that affords is people to choose how they're going to satisfy that higher level objective. And then the way we look at it is, how is that achieved? And then how is it coordinated? So you may end up getting a reaction force relative to the center of mass, but do it with a knee moment dominated strategy or equal knee hip distribution. This is the part about, I forget who talked about the distribution part, but that's where that gets interesting. And then you link it to which muscles are basically providing those torques. And now you're into, okay, great idea. This is how it was achieved. What was the cost? So we often look at energetics as the consequence of the strategy chosen. And then, no surprise, you see the net joint moments and the EMG matches, right? But there's probably higher level energetic consequences. But if you get the task done, oftentimes these are tasks that are more technical and not long distance running type, where energetics matter
Yep.
a lot, right?
Yep.
So, and with impact and things, you're preserving the system's integrity much more than you are caring at all about what the energy expenditure is. So this is the part where the energy circle might be really small on most of the tasks I've looked at, whereas the choice on the control, maybe in the agility side, to then achieve, I don't know if that helps, but I would definitely say I'm dealing with Venn diagrams with unequal circles.
Yeah. Yeah. So what I hear you saying is, for you, it's more about flexibility in the strategy that makes, would it be fair to say that someone who is more agile has more options?
Well, I think that's a capacity thing, right? So options come because you can, right?
Okay.
So this is about preparing to play. If you think about an athlete, not every person can do a triple jump at 17 meters. There's so many skill sets in there and so much adaptation of tissue that allows you to do those kinds of things. And that's where the training comes in. Your capacities aren't static. They change with time. They adapt with progressive increases in load and challenges. So now your capabilities match the task you're being asked to do in the playing field or in competition, right? So the capacities afford plan A, plan B, maybe plan C, and you practice those because unexpected circumstances are going to happen, right? And you plan for those as well, right? So there aren't a million plan Bs, right? There's a couple that work, and there's, it's not like you have infinite amount. I'm sure you can do optimization and figure out all of them, but people present, at least at the national team level, with a couple. There's like 2 or 3 strategies that seem to be really effective. I don't know if that helps.
Yeah. Super interesting. I mean, my
Yeah.
engineering brain wants to have like, oh, it's peak velocity, or it's acceleration, or it's the time it takes to achieve the task. And what I hear you saying is, yeah, okay, engineered. Like, the world's way more complicated than that. And agility is really about capacity to have options to solve a task in more ways than one. It's about flexibility. And then
What
coming up with ways to measure that, I think, is tough, right? Um, like how do you pick the
yeah,
most agile athlete in your lab?
I
What
don't really
experiment
care
to
about
do?
who's most agile.
It
You
doesn't
know,
matter, you're
it
saying. Like, it
doesn't if
doesn't,
you're
it's,
most agile or most energetic. It matters, do you have the linear and angular momentum at last contact to do the
yeah,
aerial skill? So however you get that, that's on you, right? That's a great idea. How are you going to get there? But it allows for versatile, or more than one solution. And then you're trying to map, this is what the people competing are trying to do, but there might be more than one way to get there. And this is the part where I'm finding para athletes are really interesting because they have different shifts in capacities. And so it opens your mind to what the versatility of achieving those objectives might be if you don't have certain capabilities and you have others, because there's some neural responses that are actually really advantageous for some of our para athletes, like regulating stiffness and things, that makes them more effective in generating the reaction forces they need to do the task.
Makes sense.
Kisa has her hand up. Yeah.
Yeah.
Yeah, so
Kisa.
this is definitely not my area and not something I've really thought a lot about, but it occurred to me that like one definition of agility might be like the ability to maintain consistent performance despite like variations in the initial condition. So, like you put your foot, you plant your foot on the plate like in the triple jump a little bit differently every time, and Monica says like that's robustness, but I'm just trying to like, I mean, it seems like there should be definitions of these things that differentiate them, like from each other, and maybe that's not possible, but yeah, I don't know if other people have ideas about like, how could you differentiate between like agility versus robustness versus, yeah, I don't know.
But I think you bring up a good point, because it's the state of the system, right? So, you fly through the air and you go to land again, but what's the state of the system prior to touchdown? What do you have available to you to then configure for an effective ground contact? So the state of the system is really important, in that can you, in the words of Greg Louganis, make all the right moves from all the wrong places, right? And that is what happens if you're on a springboard and, well, that didn't go well on the hurdle. Now what? I still need to get, 9s and 10s on my dive. And that's the part where if you practice plan B, you can then be really effective in competition, because life isn't always so consistent.
Okay. Awesome discussion. I put 4 words that I added 2 more words to the mix that maybe captures some of the nuances that started with stability versus agility debate. But Lena and I have, and many others have also brought up the word robustness before. And then versatility, I think, fits a lot of what Jill was talking about, maybe. Anyway, it would be fun to keep talking about this stuff. In the last few minutes, I was hoping to maybe we were going to draw all this out, but I'm probably just going to skip to the slides that have the answer, since we're running out of time. But the idea from before was that if you again, we're going from a very contrived task definition in the lab, which now we've heard from others, like that's important, right? If you have a well-defined task goal, then you can start to think about within that task goal, what does it mean to be stable or agile? And so we, in our lab, we like this simple hopping model, but we can also extend that to a foot pedal dynamometer, which you all heard about last summer, which we now have a working motorized version of, thanks to feedback from the crew. And on this dynamometer, you can just do a cyclical ankle task, and the dynamometer feels like a mass in gravity. So it's like you're bouncing, but you're lying prone on a table. Your plantar flexors feel as if you're vertically bouncing. And then we can show people what their position is on a screen. And we can also show them what their velocity is. That would create a limit cycle if we wanted to show them this whole thing. Another option is to show them the time series of what they're doing and ask them to maintain a peak ankle target. That would be like maintain the distance between the center of this limit cycle and an amplitude, right? So the amplitude in time is the distance between plus and minus theta on this limit cycle. The amplitude and velocity is the distance between the peak and the minimum and maximum values on this part of the plot. And again, you can kind of see the cartoon here. As you go around and push the pedal against the gravitational load, over here in the left half plane is where muscles are bringing the velocity back up to some set value. And over here is where the subject would relax and gravitational accelerations bring the velocity back down. So you have this interplay between muscle action pushing you up from quadrant 3 to 2, and then action of gravity pulling you down through quadrant 1 and 2. Do people following that so far?
How does the gravity work?
The gravity is programmed as an offset torque that the person feels in one direction.
Oh, sorry. You have it connected to this load. Got it.
Yeah, it's connected to a load, so you can think of it as vertically bouncing without an aerial phase. So you're lying prone, and you're only doing it with your ankle.
Sorry, gravity's happening when you're plantar flexing, so that's like stance phase?
Yeah, gravity is happening all the time, but in only part of the phase portrait are you counteracting it with a torque. So if I did nothing, this thing would just go off and out the left-hand side of the page. So over here, I'm following a flow which just comes from gravity until a point when I engage my muscles and the torque coming from my muscles, if that's greater than the gravitational torque, it pushes my net velocity back up. And then I relax, push it back up, just like bouncing would happen. So you get a rhythmic EMG pattern out of this task. And the person's instructed to just generate an initial cadence based on a metronome, and they need to touch a peak ankle joint target. And the task is stay on that metronome and target. So boop, 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 boop. They learn to use their muscles to do that. And the way that this phase portrait works is in the left-hand plane is where you are, sorry, I have it. Your confusion is because the cartoon's backwards here. The right half plane is where the muscle action's happening. I apologize. And the left half plane is where gravity's taking over. You can draw it the other way. You would just flip the sign on the theta, and that's the one that I drew out in my notebook. Sorry. Okay, so you are raising the center of mass in the right half plane, and then gravity's lowering you. So plantar flexion, dorsiflexion, plantar flexion, dorsiflexion. And then what we can do with this motor is at some point along this trajectory, we can insert a change in insert a change in the angular velocity by just programming it. So we give you a blip in angular velocity, and then the task still remains. The person still has to maintain. They have to try to get back to that boop, boop, boop. And one thing we can do to measure the stability might be to calculate the total energy of the system, which in this case is easy. It's just 1/2 times m times the velocity squared. If you put that in rotational terms, there's a moment of inertia that the person is overcoming with their torques. So at any point on here, theta dot squared times the inertia that we're applying through the motor times 1/2 is the current kinetic energy. And at any time on here, the gravitational potential energy can just be computed as mg times the delta H that comes from the change in the angle. So we know the potential and kinetic energy at all times, we can calculate it. Then we also know how much the energy is going to change when we push the person off of their limit cycle. And then what we can do is something like this, where we say, here is E0. That's the total kinetic plus potential energy at any point along the limit cycle, which has to be the same. There's a constant energy. Anywhere you are, just Sometimes it will be more kinetic and sometimes it will be more potential. But there is a constant energy in the steady state limit cycle. And then what I'm going to do is push you off of that by injecting a kinetic energy coming from a velocity. And then I'm going to check to see how long it takes you to get back. And you can measure the time constant here by just tracking the energy of the system until it gets back within some tolerance of E0. And then that lets you say something like, you can make graphs that are like E over E0 versus T. And T0 here is just 1 over the frequency. This would be a way to compare limit cycles that have different energies. Okay, so pause there. That's the idea for stability, is that set task that's got a limit cycle that's easy to define and calculate the energy of. And then a system that's able to inject energy. And you could do that at any point in the phase here as well. And ask how they deal with it in a phase-dependent way.
So if you were gonna do this with different loads, then would that be like robustness? Like how that
Interesting.
change,
Yeah,
that
or
time
maybe
would change?
versatility. I don't
No,
know.
like if you were to say a higher load and now it takes me longer to come back, or now I just can't come, like there's gonna be a point at which people can't load, they can't do, right? And right before that, it's gonna be a load that takes them much longer to get back, or maybe a squirrely path. Maybe it's not like an exponential decay.
Totally. So I'll think about it, robustness maybe in this way. Let me pick a different color. There is a outer limit, which might not be a circle,
Uh-huh.
beyond which
Yeah.
no matter what you do, you can't get back.
Yeah.
And yes, totally, Lena. You could use load.
Yeah.
You could use the load to get a limit cycle that is near the edge, but there's other ways you could do that too.
You
I
could
think
use load or frequency.
you could use frequency and amplitude for sure.
Oh God.
Frequency and amplitude are the easiest way to change the size of the thing, but you could also push them like really far and then see whether they can get back, right? So robustness to me is like, how big is the space
that you can return from.
that you
Yeah,
can
yeah,
return
but
from?
load, but okay, for each person, when you give a particular load, they're gonna be they're gonna have a different size circle, right?
Yep, their nominal
Yes.
limit cycle will be at a different energy level as
No,
the
is there a metronome? Sorry.
Yeah, there's a metronome and an amplitude
Okay, but if there's a
cue.
metronome, then they have to.
They have to return
We're asking them
within
to
a
return to the nominal limit
specific
cycle,
time.
but we're not telling them how fast or how to do it.
And it might
We're
not
just-
be circular because people might have to like,
Oh,
be a
I
little
drew that.
ballistic.
Yeah, totally. Like this thing could be an ellipse, by the way. I just made it a circle. Like
But it could be
they each have,
non-circular.
it could also be not circular, I guess, if they do weird things at different phases, but just for purposes of simple, I don't know what this circle will look like when I ask a human to do it yet. It depends on what their joint angle and angular velocity are and how they choose to exert the torque to get the task done, right? Whatever they decide to do in steady state, I think I'm just saying there's something and we can push them at different points and then measure the energetics of the transient
Okay, but
response. That's
here's
all.
an idea. Like you change
Yep.
the load and then you look at
Mhm.
the shape of that thing for a person.
Yeah.
And this is from our gate signature stuff. It's like at some point that shape is no longer going to be that shape and it's going to break down because now they're like really struggling. And I
Yeah.
feel like the consistency of that shape across the loads is going to kind of tell you the range of
Uh-huh.
somebody can use
Interesting.
that strategy. So, I mean, we see this in like
Yeah.
gate, like people use the same dynamics until it gets people with stroke, until they get too fast, and then they're like trying all kinds of stuff. That's the same as us, like people are walking across the floor, across a fat beam, and when they get to a narrow beam, then okay, it doesn't resemble that anymore, right? So you've gotten past the thing that you're good at. You can see what's my nominal strategy, what's the range of loads or challenges that I can maintain that strategy. All right, I'm liking that.
Greg, can I ask a question?
Yep.
What's
Please.
what is overall, in your view, the advantage of this setup compared to having someone do the equivalent whole body task? So like have them standing and bouncing without an aerial phase to a metronome and having a harness on them where you can perturb them by like pulling down.
Yeah, I mean, I love that experiment too.
Mm-hmm.
I think the complication of all these sources of energy now
So you
makes
could use your
the
knee joint
interpretability. Yeah, right.
to
Like I think
compensate rather
for
than
me,
just
it's just about interpretability. But where we would want to go after this is like I like the isolated joint as a start, just to try to understand whether even this framework makes any sense. If it does, your idea for that experiment would be great, because then you can ask how the multi-joint system, this gets back to versatility and some
does
of
it increase
Jill's
robustness?
ideas.
Yeah.
Yeah, totally. Like once I give you a second joint, does the time constant of recovery, like how does this time constant of recovery depend on how many degrees of freedom I give you is another interesting question, right? Like right now, just for simplicity's sake, is I would say the only reason we're doing it this way.
Right. It's
And the other
isolating
thing is
single joint. Yeah.
we can also get the muscle level measurements off this system,
Mm-hmm.
right? Like when we can really study the muscle tendon unit kind of directly. I think we're at time. There's one more thing I want to say, which is what is agility? And it just means instead of the motor pushing you off, I, through the feedback system, tell you a new task. So it's literally the same exact calculation, but this time, the change in energy is not from a perturbation down. It is to and it actually is, I drew it sort of already. It's to a new red line. And so this would look like this. And the time and you could also put the red line, again, this is energy. It's E over E0. And then I create a situation that requires a change in energy, either higher or lower. And I check to see how well the person can get to that new reachable space, how quickly.
But how quickly? When you say how well, like how quickly they can match the new target?
How quickly, yeah. So this time, which you can fit I think you can fit a first order thing to this. I don't know if it'll be first order. That would be sweet if it is. But you can fit a time constant, or you can measure a time, or you can calculate the average power over this time, which is the change in energy divided by the time. Those would all be equivalent ways to get at and then higher numbers, an average power would be better, more agile. Shorter times would be more agile. And then the stability one is, again, I bump you to a new energy, and I check to see how quickly you get back to E over E0 of 1.0, right? This is the nominal limit cycle. Okay.
I want to throw learning into this because I'm not sure how
Yeah.
quickly you learn is as important as the quality that you acquire over time. So be careful about making how quickly you get something the goal versus how robust perhaps the solutions are.
Yeah.
I don't know
Yeah.
what word to use anymore on anything.
So you'd have to have repeated measures of this and see how well they actually match the targeted.
Or how long it
That's
takes to
right.
come up with a
Energies.
viable solution that fits within the performance margins.
Mhm.
Right? Because that would be
Agreed.
good. So it ends up being what's good enough. And then this is always a good question. Have you prepared the person to play? Right? Is it good enough for the challenges you put forward? So that it's in their skill sets to put, to do what you've asked them to do. And this keeps them out of risk. Sorry, I'm doing core 4 on you guys here. that's the context here, right? Of the learning and the risk and the reward, right? So
Yeah, the idea of like how well people people change over time is
mhm,
totally within reach within this paradigm too. I think wouldn't be the
yeah.
first experiments we do, but you're right that if like, let's say people came back, well, first of all, we'll give them repeated trials of this, I think, even in the
Mhm.
first experiment, but you could have them come back multi-session, right? And you can ask whether or not in this context of the task goal, which is they know they're going to see the same task again, can they make their time constant better? And then how are they doing that, right? So the change in the time constant over repeated visits would be also pretty interesting.
But I think
I-
time constant alone doesn't fully capture performance is also Jill's point, because
Yeah.
you would have the distribution of how well they actually matched that target, right? At all, like did they get
Yeah,
there?
like how I see, like how good they are at even following the instructions. Gotcha.
Right, yeah.
Yeah.
I think the other part that I struggle with on this too is I can't think of movements where getting the kinematics the same is a goal as compared to getting the force production the goal, right? Do you know what I mean by that? Because like in this task, the goal is to maintain the kinematics,
Yep.
and
And
you know
then,
you
but
can get that
Oh,
multiple.
yeah, yeah, yeah.
well,
You know, I
in
mean, in this particular one, right? Versus
yeah, so
generating
are you
force to create a
Yeah.
whole body movement. I'm just trying to say
I-
there may be value, but this is after you get through the one joint, can I measure stuff, I guess.
yeah.
Mhm.
Yeah, I hear you. Like we struggled with whether we should give the feedback on torque versus on joint angle. And right? Like cuz you could show people their torque through time instead. And then you could solve for the torque through time they need to maintain a limit cycle and ask them to just attend to that torque.
I
So that's,
mean,
you know, that flips the task to a explicit force control versus an explicit position control task. I don't know. I
It
don't know whether
depends
you
on
find it.
what you're trying
yeah.
to model, but I always think about pictures and they're like, don't tell them exactly how to throw it as long as their like direction velocity's good at the release, then you're fine. But when you don't have when you have 1 degree of freedom, it's hard to dissociate a lot of these things.
I also suggested a springboard version here if you wanted to play around with the energetics, where you have a deformable surface and interacting with it.
That's
It's
fun.
comments up there. That might be a functional way to play with this also.
Uh-huh.
Yeah, that's a super cool idea. And again, that would be like an
Where,
energy well that's part
yeah.
of the system but not attached to it that the person
Mm-hmm.
could give to and
Mm-hmm.
take from, and you know, like
Yes, you got
which I
it.
think
You
happens a
know,
lot
Greg's
in
into that.
animal
I
world
like
too.
this because it's in your interaction with your world, right? What can you get out of the environment you're in to get the job done, right? So it'd be great. Happy to talk about this at length.
Okay, folks,
Well,
we're over a bit. I want to make sure I can hang out, but other people might need to go. I should also probably go.
Yeah, we should probably wrap up for today. We'll have
Okay.
more discussion in the future.
Thanks for listening. Hopefully you got something out of it. Fun discussion. I'll try to share these slides once my computer is functioning properly again. Right now I'm running off like 300 megabytes of hard drive space because my Dropbox tried to overrun my computer when I came back to the US. So just hold tight and I will send the slides through the Slack at some point. And see y'all around, I guess.
Cool. Thanks,
thanks.
Greg. That was
All
fun.
right.